Hello friends of Wakefield Accelerators, welcome to my channel. In this video I will show you how to design a gas cell for Wakefield accelerators and run a simple simulation using Ansys Fluent. If you're not familiar with gas cells, here is an example. So this is one of my previous designs for a gas cell. It consists of a slit nozzle, so if you watch my previous videos you will understand what I'm talking about if you don't know. So it's this part, which you can see it also here, is a slit nozzle part, which you can have it or not, so depends on you. The reason why I have it, because on the bottom there is a flat region where I used to generate nanoparticles. Again, if you want to see more about this design, you can search on the internet nanoparticle assisted laser Wakefield accelerator, and you will understand exactly the design. So it consists of this slit part with a flat part, which you cannot see it here, but the design is pretty similar. And the actual gas cell is this region that you see it here. So this this part. Now, if you want to design it without this part, you can just put an inlet somewhere, and pretty much you can have a gas cell. I prefer to have this slit part because I observed that the gas density profile is much more uniform here in the gas cell. The example that you can see here has also a movable part, but the gas cell that is actually here, and also the one that we will design and simulate in this video, is fixed length. So before you are doing an experiment, you will know what length it should be, it should have, so you will design it accordingly. Also, there is the option, of course, to make it 10 centimeter, let's say, and here you will design a tube that is going inside the gas cell, and again you can have a fixed length gas cell. So it's up to you. Now here it's another view of the gas cell. Here is the inlet on the bottom. The inlet is, there is nothing really special about it. It's just 2 millimeter diameter inlet. And here you can see is a pressure transducer, which is used to check the pressure inside the gas cell. If you know the pressure, of course you know the density. It's easier to convert from pressure to density using ideal gas law. This part has to be removed and replaced with a window for the experiment. Now the dimension of the gas cell in this case is 3 centimeter by 3 centimeter, and the slit part is 2 centimeter by 9 centimeter length. It's up to you how big you want to make the gas cell, depending on the laser energy, depending on the needs. You can have windows or not. It's good to have windows because you can align better the gas cell. Also, you can see the interaction, the interaction between the laser and the plasma, and extract whatever data you need. Now there are pros and cons using a gas cell. It's up to you if you want to use it or not. In the past years I designed a replacement for the gas cell. So I designed what I called the chimney nozzle. Again, you can find a video on it. It's still not tested. I will test it soon and see how well it will behave. So the quality of the electron beam, how well I managed to control the density profile, and so on. And depending on the results, it might replace or not the gas cell. It has many more advantages. So a chimney nozzle has many more advantages over the gas cell. But it's up to you. If you really think you need a gas cell, here is an example how to model it and run a fluid dynamic simulations using Ansys Fluent. So let's get started. In this case, just to save time, I will just use a previous case that I built for a chimney nozzle, which I'll modify it accordingly. If you are for the first time on this channel, please watch that video to learn how to model this nozzle. So what I will do is just duplicate a previous case. So duplicate it will do exactly what it says. It will duplicate everything that is in this case. Now let's modify. So gas cell simulation. Give it a unique name so that you can recognize it in the future. And now the meshing part, we need to reset it because we will not. We don't want to keep the previous values. The same for Ansys Fluent settings. We will start fresh with those. And now the geometry, double click or right click and open using Design Modeler or Space Claim or whatever is available there. All right, so what we will do, we will modify this part, so what is called a box. So this part, we will make it bigger, 1 by 1 centimeter. Then we will modify this part, we will make it shorter so that the distance from here, from the bottom to the outlet, so the outlet will be here, will be about probably, let's see, about 10 centimeters. It doesn't have to be fixed length, it doesn't really matter. So for the gas cell is you don't have so many constraints as in the case of a slit nozzle or conical nozzle. Of course this will be actually the gas cell part. So this will make it 10 centimeter long. All right. So let's start with the box. We will modify this one. So we said we want 10 by 10 by 10. So let's make it like this, 10 by 10. Okay, generate. All right. So since this part is connected to this surface, of course it will modify as well. All right. Now we have here a plane, and let's put it. So this is 1 centimeter. Let's put it for simplicity at 9 centimeters. So the total length from here to here, it will be 10 centimeters. So or you can make it even shorter, but let's keep it at 10 centimeters. So it will put 90 here. All right. And now let's modify the slit part. Let's make it 8 centimeters by 2 centimeters. So let's see. I can't remember. Okay, so age is okay. So 40 millimeters, 40 millimeters, and 5 millimeters and 5. No, actually 10 millimeters, because we said we want 2 centimeters. All right, generate. Okay. Yeah, so this is the slit part. Okay, now let's modify the other box. So this one will be again at 90 millimeters, and the Y component, which is the length of the gas cell, it will be 10 centimeters. The Z component, it will be 30 or 3 centimeters, and also the other part, it will be 30 centimeters. And now let's translate the box so that it will be, you know, in the middle of the coordinates. It's better to do like this because it's easy to orient the other elements in case you want to add them. Okay, so now let's translate it -15. Okay, and -50. And yep, so this is pretty much it. Okay, so you can see this is almost done. Now let's do something else. Let's put the inlet. So the inlet, it will be from this side. You might want to put it from the bottom, but from my previous experience, I discovered that it's not a good idea. So if you put it exactly in the bottom, not only that you cannot build the gas cell as I mentioned before, you know, to generate nanoparticles from the bottom through laser ablation, because there you have the inlet, but also the inlet, if you have it here, it will generate a gas density spike exactly in the middle of the gas cell, and it's not good for laser wakefield acceleration experiments. So I discovered that it's better to put it sideways, so like here, and the flow is going through this part, and it mixes uniformly by the time it reaches the gas cell part. Of course, the outlets that will be here, or the pinholes, whatever you want to call them, will play a big role. Okay, so we have this one. Now it's very easy to build the inlet. Click on the surface, and now go to sketching. And as soon as you go to sketching, a new plane, if you check it here, is generated, plane 5. And on this plane, on the surface, we will draw a circle like this. Alrighty. And now let's put this circle exactly in the middle of this surface. So this is 1 by 1 surface, or a square. So if you go to dimensions, okay, click on vertex, click on this, okay, and vertical, click on vertex, click on this one. So all you have to do here is just 5 and 5, and now it's exactly in the middle. And now let's define the radius, the diameter of the inlet. Let's say we want a 2 millimeter inlet. Okay, we have done this, and the inlet, it should have a throat. So what we do, this is the circle, create, extrude, the geometry we chose, sketch, add material, direction vector, we need to define it. So you want in this, so this will point in this direction you want, apply, and here the length, let's say 1 centimeter, and it already shows how it looks like. So that's to give you an idea before you generate. Okay, of course you can always modify it, so it's not a problem if you press generate and discover that it's not what you want. Yeah, so this is the inlet. Great, and now we will draw the outlet or the pinholes. Okay, again, press surface, press this, click on the surface and go to sketching. Boom, now it's another surface generated. You can see it here, so plane 6. Another circle, like this. Okay, let's define it. So again, horizontal, we need to put it exactly in the middle of this thing, and the vertical. Okay, and the diameter, click, that's it. Diameter, let's put 3 millimeters, and this is 15, and this is 15. So it's exactly in the middle. And what we will do now is we go to modeling, click on this one, create, extrude, but we will not extrude anything, but we will imprint a surface on this one so that we can separate the pinhole from the rest of the surface. So this surface, it will be wall, and this will be outlet. And to save time, instead of drawing the outlet on the other part of the gas cell, we will just imprint the surface at the same time here and the other surface. So apply, and now instead of add material, we will choose this one, imprint surface. Okay, direction. Okay, so let's see what direction it will be. So it has to go in that direction. So this one points in the right direction. Apply, and extend type through all. So through all means it's going through this one and this surface. Okay, now let's press I think the direction normal, and let's press generate. Okay, and everything is fine. Here should be the check mark, and let's see, if you press on this surface, you see this one is not selected. If you press on this one is selected. And let's check the other surface. So again, press here. Good. So this is pretty much our gas cell. Now we have to mesh it. Now, of course, if you want to see the density profile, you need to define a region outside this part. I will not do it now because I want to save time. So you can modify it in any way you want. As time as you know these steps, how to define these small parts in the outlets using the imprint phase, then you are good to go. Okay, so this is the gas cell. Now it's good to remember that the outlet, the middle of the outlet, is at 10 centimeter plus 1.5, so 11.5 centimeters, because you will take line outs exactly through the middle of the gas cell. There is the region of interest. So the laser will go through one pinhole, and through the other pinhole it will exit together with electrons. So you don't care about the density profile in other part than through the middle of the gas cell. Okay, so we could define now the boundaries here, but we will do it in the meshing program. It doesn't matter where you are doing. Okay, we close this one. Everything is fine, is checked. Save it, just for peace of mind. Now let's open the meshing program. All right. Of course, we cannot use the default mesh. The default mesh will combine whatever is the program thinks is suitable, but it's not the best. So right click, insert, face meshing, and geometry. We select all the faces just because it's simpler for me. If you know what you are doing, you can choose just certain surfaces, or you can split the domain in multiple bodies and apply different mesh. It's part of the experience. Okay, so insert, and now method, and geometry is this one. Oops, I didn't keep it. One body, because it's an entire body. And method is not automatic. We will use multi-zone. Click on mesh and the quality and smoothing high. And mesh metric, I want to see statistics about element quality, and statistics will be here and also plotted here when we finish meshing. Okay, now let's define the inlet. So we go here, click on surface, click on this surface, right click, create name selection, so pressure inlet. Okay, now this one, right click, pressure outlet 1, because we have to. All right, and let's go the other side. Okay, select this surface and define it as pressure outlet 2. Okay, and now these are the walls of the gas cell. So you see here, so these are the walls, top and side. So we will select all of this. So if you press on the keyboard control, you can select multiple surfaces, or you can define one by one, but just to save time, I select all of them. Okay, like this, and like this, and okay. So of course I made a mistake, so I have to reselect them. Okay, right click, and let's call it wall gas cell. Okay, now it's always good to check. So if you put it in a convenient perspective, pressure inlet points there is fine, pressure outlet, pressure inlet, pressure outlet, the other one, and gas cell wall is red, everything, so everything is fine. I don't need to define the rest of the wall, because if you don't define it, by default everything that is outside is recognized by the program, by Ansys Fluent, as wall, and is defined automatically. Everything that is inside the gas cell and is not defined in any way is recognized as interior or part of the fluid, so you don't have to do much. Okay, we finished this part. We don't have to do just the meshing. Now we keep the default just to see what it's doing. So let's press update. Now this is a big volume, so most probably you will not be able to run an accurate simulation with a few hundreds of thousands of cells, but you can try it. Always run mesh independent studies. So increase the mesh to see if the solution is affected. So maybe 1 million cells, which is the limitation of the Ansys Student, is enough, and you might be able to run the simulation without any problems. So just try it. This is how you gain experience. Don't follow somebody, you know, word by word. Improvise. You have nothing to lose. Okay, so this is the gas cell, and here we can see the number of cells, of course, is way too low. So let's change here 0.000, let's say 5, and right click, update. Yeah, it will take a while because it's quite a big geometry, so the number of cells will be very high. Okay, we wait to see. Okay. Okay, now it's updating, so that's why it looks like it's frozen. And now we have about 3 million, almost 4 million cells. I told you it's a huge geometry, so it's expected. I will just leave it as it is so that I can proceed with the tutorial. Feel free to check or test other options. Okay, so everything is fine. I see here I'm satisfied with the quality of the mesh, number of cells. We pretty much finished what we are supposed to do here. We close it. Everything is fine because we see here check marked. Also, sometimes it's not necessarily true. There is a bug in the Ansys Fluent, or Ansys Workbench more exactly. It shows checked, but when you try to import in Fluent, you'll get an error, and it doesn't say why. So if you get that error, most probably is because of the mesh. So go back and remesh it using Cartesian meshing, or changing whatever the geometry, changing the way you mesh it and so on. Mesh size. Okay, so let's open Ansys Fluent. Now here, if you have done the simulations, the previous simulations that I showed in the videos, you will do absolutely the same steps. So here is no change. The only thing that, I mean, the main work will be in the drawing the geometry and mesh. There is the main work. In Ansys Fluent, we will never change much. Yeah, if you have more boundaries, like we have here 2 outlets, you have to define them individually. But pretty much the rest of the settings, they stay the same. So double precision, start. All right, and now it imports the mesh, and it runs some checks. Okay, this is the mesh, and here it points towards the inlet, here points towards the outlet. It's good to check this in general, just to make sure that what you expect is here. So yeah, these are the 2 outlets, and this is the geometry. Okay, the scale is good to put it in the units you draw it, just to visualize better. Close, check. This will give you the extension of your domain. Now this one is from, so this is good to remember it. So y is from minus 5 centimeters to plus 5 centimeters. Okay. Okay. Report quality. If you need to define the units, just check previous videos. I usually change the density. Instead of kilograms per cubic meter, I change it to atoms per cubic centimeter. This is relevant for laser wakefield acceleration experiments. I will not do that now, just to save time. The solver, as always, density based, steady state case. We will not do transient for now, maybe in the future videos. Now models, always energy equation is solved. By default is viscous with the default settings. I never change them. I discovered that they work best, so there is no point to play with those unless you know what you're doing. Okay, and materials, double click, create edit, Fluent database, and choose the material that you want to use in your simulation. I use helium because helium or hydrogen, these are the main gases used in laser wakefield acceleration experiments. Feel free to use whatever you need in your experiment. And from here, ideal, okay, close. And now double click on helium. And instead of density constant, choose ideal gas, press change create, close. And if you don't know how to define things here, press help, and it will open the documentation for Ansys Fluent, and it will give you details how to, if you want to change, how to change them. So this is valid for the rest of the things or the windows that you open in Ansys Fluent. All of them will have help, and it will give you information. What does it mean? What to change and how to change. Okay. Now, okay, let's go to cell zone conditions. Operating conditions is 0 because the gas cell is surrounded by vacuum. And double click here on fluid, and by default is it takes air. You need to change to helium. Don't forget this step because you run the simulation with air while you think is helium, so be careful about this. Close. Okay, boundary conditions. Now let's define the inlet, pressure inlet. Now for the gas cell, since we have quite a huge inlet, is 2 millimeter diameter, you don't need to put huge pressure. I mean, you can try with a huge pressure, but it's pointless because you have here a confined volume. So you reach huge densities even with modest inlet pressures. You can try with, let's say, 200,000 pascals, which is about 2 bar, and initial pressure here just slightly less than the total pressure. It doesn't really matter this value. It's just to move the flow or to start the flow in the simulation. I prefer this specification method for turbulence. Check documentation to understand how you define it and what does it mean. Okay, and if you have a pressure, a temperature for the inlet, it will define the gas temperature. You can change it from here. I don't change it because the gas is room temperature most of the time, so there is no point to change that one. Close. Okay, now we have outlet. For outlet we have two outlets. We have to define for both of them, so 0.001, and here again diameter 5 and 1. Now here, if you'll watch a previous video where I talked about divergence of the solver and how to avoid it or how to correct for it, you don't run the simulation with this very low vacuum pressure. You'll put something like 1 bar or 100,000 pascals, and you run the simulation, and as soon as the solution stabilizes, you change it to the desired outlet pressure. Right now I will keep it as it is, but most probably it will start diverging. So just watch that video how to correct it, and you'll see it's very easy for this case, at least. For other cases it's not that easy. Okay, apply, close, and the same here. All right, the same. Apply, close. At methods, we don't change them. By default are this. Here by default are this, we don't change them. Monitor, residual, I use 10 to minus 5, not 10 to minus 3, even if the residuals, most of the time they don't reach 10 to minus 5. I just put 10 to minus 5 because it's not the main criteria to get an convergent solution. So I don't particularly care about the value here. Okay, and report plots. Okay, new surface report and facet maximum. It's not really important what you choose there, as time as you choose something to monitor. Density, and you can choose at one of the outlets. Okay, add. Okay, we can delete one of these, we keep only one. Okay, close, and now we can initialize. Okay, and what we can do now is take one line out through the middle of the gas cell, so through the outlets, and that is done through line rake, and we have in Y direction, so it will be exactly through the middle. So X will be Z will be 0, X is the height. So you remember when I said that height, and it was 9 plus 9 centimeter plus 1, so plus 1.5 centimeters, so 115 millimeters. 5, and the domain is between minus 50 and 50. You can always change this value, so don't worry about if you define it in the wrong way, you can change them, so it's not the end of the world. Okay, let's give it a name here. I call it X0 because it's exactly through the node, and let's try to create it. Create, close, and now let's plot it out of curiosity. Plot. Yeah, it looks like this because we didn't choose properly the coordinates. So 0 deactivates, 1 activates, as always. So with the initial values, This is how it's looking like. Looks like a Gaussian. Of course, it will transform into a flatter profile when you will reach the final when you reach the convergence. Okay, and now calculation activities. If you want autosave, which is a good idea, autosave every 1000 iteration or 2000 or whatever you want. You can keep all of them, or you can keep only the most recent files, like the last 5. The idea of saving periodically this is so if you don't supervise your simulation, so you just let it run overnight, for example, and at some point the simulation goes wrong, it starts diverging, then to save time, you just go here, file, import data, and you can save a previous saved data file, and you can run the simulation from that point, and you can save a lot of time. So this is especially for huge simulations where you can wait for days or weeks even to get it done. So it's a good idea to have this option checked. Again, it takes some space on hard disk, so make sure you have enough space. Okay, now run calculation, press check case, and if you forgot something or you did something wrong, usually you get here a warning what to correct and how to correct. Everything is fine here. Now the number of iterations, I don't care, you can stop it anytime, so you can put 1 million iterations to run the simulation. If you reach the convergence, which is the criteria for convergence are here. Watch previous movies. Each time I try to mention this if I don't forget. So as soon as you have all these 3 criteria met, then you reach convergence. Okay, and you don't have to do anything. Now I mentioned that the surface, that the line out that you draw, you can modify it all time, anytime. So you have it here on the surfaces. If you double click on it, you have here again, so you can change these values as you want. So don't worry if you didn't define it properly initially. Okay, and if everything is fine, okay, file, save project. Just for the peace of mind, it's saved automatically anyway when you start the simulation, but I prefer to trust me more than I trust the program. Okay. All right. Now press calculate. And now the simulation starts running. You watch the residuals. Ideally, they should go nicely down. They shouldn't go up. They could go up for a little bit, and after that they go down. But if it's going constantly up, so it reaches, here 10 to 1, 10 to 2, 10 to 3, then it's clearly it will diverge. The solution will diverge, so you can stop it and make the correct things in the simulation, like I've told you in the video about the divergence. And here is the solution is monitored at one of the outlets. So just watch this and watch this, and you just let the simulation run. And when it's run, you will use the next step. So you will save it and you go to the next step, so to the results, and from here you'll extract whatever information you want from your simulations, profiles and lineouts or whatever you want to extract. I extracted here one line out because I like to check periodically the simulation to make sure everything is fine, because if I try a new gas target, I want to see if I get the density profile that I expect. You can see very fast if it's okay or not. It's just a part of the experience. So if you plot, you'll see it. It's just experience basically here. You'll know what to expect, so you don't need to run a simulation for days on days to get something that will tell you that the gas target works as you want or not. So you can get an idea much sooner. Okay, so this is pretty much done. So this tutorial is pretty much done. Thank you for watching. If you want to support future video releases, check in the description of the video how to do it. Thank you for watching, and I hope you enjoy it, and see you next time. Bye bye.